Hello and welcome to the first installment of the 2017 ASPRS GeoByte series. I would like to remind everybody that this GeoByte is being recorded and will be available on the ASPRS website in approximately 2 days. Our first installment will be on open source statewide LiDAR visualization in web browsers presented by Howard Butler. Howard, you ready?
Yep, thank you. Hi, thanks everyone for tuning in, and hope you'll find out some interesting information on how to attack the problem of LiDAR data management and visualization in web browsers. My name's Howard Butler. I own a company called Hobu Inc., and we're located in Iowa City, and we focus on open source software engineering for LiDAR and point cloud data. So we have 3 open source projects from which we're very active in and lead. The first one is the PDAL or Poodle open source project, which is used for data translation, processing, and filtering. The second one is called Entwine, which we'll be talking about today, which is for point cloud data organization. And the third one is Greyhound. Spatial in general. So we're active in the GDAL open source project, which is used in many places for data translation, raster and vector data translation. Very active in the map server, map rendering software, which is used for OGC services and map rendering. And we also support and maintain the LibLas software library, which software is used for LAS management and data processing. So many folks in this particular call probably have some familiarity with LiDAR, but I wanted to just kind of give the short pitch overview. So LiDAR is essentially a high-performance rangefinder. So rather than our kid with his rangefinder looking to find out how far away the pin is from where he's shooting, a high-performance LiDAR system might capture 100,000 points plus per second. Each one of these points is a discrete measurement. It might have other information attached to it. And what's returned is a point cloud, so a series of individual discrete point measurements that can be visualized and interacted with. Software processes can run algorithms on them to attempt to extract information, use them for measurement, and so on. Point clouds, besides the XYZ or just the distance measurement, also provide or can often provide other measurements, including intensity or reflectance information, color information like red, green, blue of the particular target point, potentially the scan angle at which the point was acquired, maybe a location confidence value if the point cloud is coming from something like a dense matched imagery instead of a LiDAR source, normal vectors, geometry, return information. Softwares might attach classification or timing values to them. So point clouds, it's important to remember that point clouds often have this other information besides simply an XYZ value attached to them. And in LiDAR communities, they're often managed as a whole instead of simply just XYZ points. But point cloud data management is extremely painful. So large area collections of point cloud data might have thousands or tens of thousands of tiles or files. The usual scenario for working with point cloud data is to cut it into bits and work on each individual little bit. It's often you simply just have too much data, so to work at the desktop scale becomes very difficult. Working with software to be able to manage and interact with these indexes of software is kind of painful. The data itself is quite variable, so you have variability in file formats, just simply versions of the formats, different file versions, kinds of formats, different sensor types might produce different kinds of data. So as we're seeing in Geiger mode systems versus linear mode systems, the Geiger mode systems tend to have a different format they tend to operate with that is not necessarily LAS, although the attributes and so on in them tend to be quite similar. The content of these point cloud data might be different. Of course, in this community is very familiar with the LAS format and the benefits it's had in standardizing some of these attributes, but other point cloud communities, especially in the dense match imagery world, A point cloud world might not necessarily have those particular attributes. And then your typical sort of data management issues of coordinate system, metadata, how it was acquired, geometry acquisition, so on, are always going to be there. And just the difference in the point cloud types itself. Is it a LiDAR data, structure for motion, and so on. So it's very difficult to know what you're getting. It's difficult to manage individual tiles, and this burden is placed on you as a user to interact with these very large collections of data. Point cloud data is not really raster data. So, the typical toolbox we would reach for in raster data would be to create overview pyramids, but for point cloud data, they don't quite stack like that. So if you try to tile the data by a common geometry, you end up with uneven density. If you try to tile the data by a density, you end up with an uneven geometry. So this adds a unique kind of twist to the organization problem for point cloud data. There aren't convenient compression capabilities kind of fluent within the software industry-wide. So there isn't really a JPEG 2000 or a JPEG or deflate, gzip compressed TIFF kind of equivalent for LAS data, or well, there is for LAS data, but for LiDAR and point cloud data in general. So there is LAZ, of course, which is openly specified, but not all algorithms are available, or compression algorithms are available in all software platforms. And so this is a challenge that users have to maintain and deal with. And then beyond LAS, which has had good penetration, and at least in the LiDAR industry, support for other formats tends to be a little bit limited. So if you're doing something a little bit different, you have data format challenges to get over. Software is typically, software organized as thick clients, which is the usual mode for interacting with raw point cloud data. People reach for software. Your thick software client, typically very capable. You can buy as much hardware as you can afford and interact with the data very quickly. You just need a copy of the data locally. You don't need network to interact with the data. But the downsides of that, potentially those software, you need permission to install them. Of course, not all of them are open source, but you might need permission from your administrator. You might have a lockdown machine. Licensing can potentially be an issue. That hardware can be very expensive. A very high-end workstation for doing lots of LiDAR exploitation might potentially be a very expensive piece of hardware. And that data management burden is placed entirely upon you to interact, copy, move, and manage the data. Thin clients, on the other hand, like a web browser, have the advantage of data and software ubiquity, right? So go to a web page. You have the software right there by going to the web page. The deployment is a single deployment. You upload a new version of the software to the server that's serving it, and that's available for everyone. There's very little data management for a user, so they connect to a web page, and that's it. They don't have to manage lots of little bits of data, and of course cost is lower, and they don't have to ask permission to install any software to interact with the data. In some environments, this is very important. The downside, however, though, is thin clients, at least certainly in browser scenarios, the variability can be quite large. So some browsers are quite capable and have lots of hardware behind them, and others don't. You end up with a software application that's dependent upon a network, and that might not work for your needs. And you're potentially constrained by the browser, right? So the browser imposes some rules on how software can interact with it, interacting with mouse, interacting with a touchpad, so on like that. But each has its niche. So the thick clients, tend to do very well in heavy kind of interactive exploitation scenarios. People who are doing lots of data editing, workflowing data production. These software tools are, allow people to apply very specialized algorithms to the data and essentially have a workshop or a workbench to interact with the point cloud data. Where thin clients have an advantage is in scenarios where people want to do visual verification and quality control, simply just look at raw point cloud data itself, do measurement and interact with the data, and be able to do collaborative visualization and collaborative markup of the data. So kind of large-scale overview type applications and interaction versus kind of smaller scale workflow exploitation. The thing that is making the thin clients become much more viable for these sorts of scenarios is the proliferation of WebGL technologies inside of web browsers. So WebGL is OpenGL, which is specifically for web browsers, and it's equivalent to the OpenGL embedded specification 2.0. And so this equivalence has some benefits. So OpenGL ES2 is the equivalent of WebGL, and OpenGL ES2 is what's available typically on your phones. And so software that's targeted toward these particular standards has the opportunity to work both in a web browser and on phone systems. So your Internet Explorer 11, recent Chrome, Firefox, Safari all have excellent support for WebGL. Why do you want to use WebGL? The first and foremost is you get the ability to do hardware accelerated 2D and 3D rendering without having to have a specialized application to do that. So that means no plugins to install. And so while there is certainly variability in the quality of implementation of WebGL across the browser vendors, and you can still kind of kill your browser, the promise of being able to do a lot of rendering of data in a browser is becoming much more viable. Additionally, WebGL allows you to interact with this hardware accelerated rendering using JavaScript, which allows a much broader audience of software developers to be able to develop for it. And WebGL is viable on your phones as well, although the hardware specs tend to be quite a bit lower than your typical desktop or laptop. But the ability to target a WebGL platform and have good coverage of more than simply just a browser on a desktop application. Commercial vendors have been jumping into WebGL all over the place. So Mapbox vector tiles is maybe a technology that many of you have heard of. The Cesium open source globe environment is a WebGL renderer, lives entirely inside a browser. Esri City Engine and Arc Online are jumping into WebGL and hardware accelerated browser-based applications. And of course, Google Maps and Google Earth has been doing they've been doing this for quite a long time. So our challenge is, how do we visualize and interact with an entire collection of LiDAR in a web browser? Why do we want to do this? So the first one is the URL is simply a better, much more convenient data management tool. It's only one. Our users only need to manage one piece of information, which is where do I get the data from, or where do I interact with the data, and not deal with thousands of tiles, not deal with file formats, not deal with all of the pain associated with managing all these bits of data. A web story also allows us to provide a common security and access mechanism to our data. So if we have sensitivity issues with our data, we can use the same tools and software for managing security with those systems as we would with any other application. It provides us a fairly well-known software scaling story. We have web servers. We need to provide the infrastructure to provide web servers. It allows us to have a pluggable infrastructure so we can reuse or repurpose this web application in other bits of our software system. And of course, cloud environments have really kind of pushed people this direction in terms of looking at putting these very large collections up close to lots of computing and lots of storage, of which LiDAR is an excellent fit. Also, web services is a well-tread path in other geospatial domains. So whereas raster and vector tile services are starting to, raster tiles certainly, and vector tiles more so recently are becoming very well known in geospatial domains. And then other OGC services like coverage service and WFS and sensor service, these are all web service stories where people are using web services to, to allow them to manage large collections of data and be able to build applications on top of them that allow people to do various things without having this data management required. So what are our requirements for point cloud web services? The first one is our web service needs to be lossless, and we're going to define lossless as every point we put into this thing, its exact position and all of its attributes need to be able to be returned to us. if we're going to take the pain of organizing and setting up one of these services, anything that potentially false points through the bottom, modifies the data in any way, is not necessarily beneficial to us because we don't really know all of the applications that would potentially use this service. We also want some kind of level of detail access. So for rendering clients or visualization clients, you know, a way to progressively interact with that data is important. And you know, a typical visualization technique is something called an octree. Octree style access to the point cloud data would be really great. It doesn't have to be an actual implementation of an octree, although that might be helpful as well, but we want to interact with that, we want to be able to interact with that data in that fashion. We want to have a flexible data schema, meaning you know, the attributes I showed at the beginning with, you know, X, Y, Z and intensity. There are other dimensions besides just the typical LAS dimensions that this point cloud service might need to be capable of speaking, and we don't want to be limited to one particular format. So, you know, more like a database in that the user can construct their own schema for whatever dimension types that they need to manage. And point cloud data are very fluffy. We want some kind of compression technique that allows us to send data over the wire in as compact as reasonable, but we want that compression to be openly specified, have a free implementation, that's also nice, and we want it to work on both server and client side. So for client side, that means supporting it in JavaScript and web browser applications. Server side, you know, we have our own choices on whatever software environments that we would operate in there. We can't just do tiles though. So the consumers of our point cloud services need to be able to control the pace at which they fetch data. So a challenge with the tiling system in point cloud data, as we mentioned earlier, is if the requesting client can request by density or by geometry, they might not know the other. So one can imagine a software client in, you know, your 2G environment, you know, out in the middle of the United States, not having good network connectivity, but you still want to be able to zoom in and get some point cloud data. A fixed tiling scheme might not necessarily work in that well in that disadvantaged network environment. And so a software client that knows it's in a disadvantaged environment can control how fast or how slow it's going to download data. Additionally, browser capabilities are quite variable, and so some browsers, like on your cell phone versus something on your desktop, might choose to request data at different paces. And so the software needs to be able to control how fast it gets it. And the software needs to play nice with existing infrastructure, so that for cloud environments that might be something like an edge caching solution. We don't want it to consume we don't want a very big heavy server that consumes lots of resources though. So to give you some background on scope of these particular collections, so Iowa captured its LiDAR, you know, 2007, 8, 9, 10, 11, had a range of dates that it acquired its data. It's roughly 37,000 LAZ tiles, 2+ terabytes in size, you know, 170 billion points in scope. Denmark is another very large collection, a contiguous collection of 30,000 files, and you know, 2+ terabytes in size. And you know, another country, Netherlands, you know, 41,000 files, only 1.5 terabytes in size because it's only XYZ. They didn't acquire or pay for, I think, the rest of the attribute information for that particular collection. And then Minnesota, again, another 30,000 point collection of files. So we want to be able to provide a software application that allows our users to be able to visualize and interact with that data, or additionally write software services that software tools that can directly interact with web services for these very large collections of data without having to do lots of data management themselves. So what does the software need to do to achieve this? So the first step is it needs to organize the data in some fashion to make it so that the data could be hierarchically queried and is stored in a way that is both lossless and compressed. We need some software tool to be able to serve the data in a way that a client can control the pace at which they select the data, and the client can control the organization of the data as they fetch it. And you know, an optional bit is to be able to provide some way to view and interact with the data. So that first organized step is we want something with level of detail. Ideally it's compressed because the data are fluffy. Lossless, as we said before. It'd be really great if it worked fast and worked in parallel so that we could do things in cloud computing environments where things can, we can pay for more scale. And as mentioned earlier, needs to support any data schema. The serve piece of software really only needs to support three things. One is an info query or a metadata query. Tell me something about this Minnesota or Netherlands collection of data. What is its bounds? What is its coordinate system? How many points should I expect to be able to fetch if I'm going to grab the entire thing? A way to read the data, select for a bounding box or a bounding cube and some other information and fetch the data. And then something called a hierarchy query. So some clients, as they're querying, might be able or might have value in peeking ahead and knowing what the shape of the data is potentially below them in a data tree. And then that might change how they would query the data so that they would, instead of making lots of little requests, collapse together requests into bigger requests. Fewer round trips potentially might mean a faster application, and it's up to the applications to be able to make those choices. And so this particular request allows them to do that. For viewing, we want a piece of software that's geospatially aware. We, know a little bit about coordinate systems, know a little bit about, more than simply X, Y, Z. We'd like to be able to blend data together, so other web services, like especially WMTS tile services or vector services potentially, we'd like to be able to interact with them with our point cloud data. We don't want an application that just completely lives on its own. For collaboration and interrogation type activities, we would like to be able to essentially spatially bookmark a view of data and provide some capability to interact and measure the data. So this open source software that achieves the organization step of these three things is a software called Entwine. Entwine is open source released as LGPL, so meaning so if you were to distribute Entwine, you would also need to release your modifications to that distribution, but it doesn't require that you release all the software that touches Entwine, for example. It's a cloud-friendly piece of software, so it speaks Amazon S3 or Dropbox. It's very concurrency-friendly because the challenge it undertakes is to organize large collections of point cloud data along a space filling curve. In our case, it's a Z-order curve, and which allows applications to query into the data. It uses standard compression, like it uses LAZ style compression to achieve its compression technique, and stores the data losslessly. The server component is a software called Greyhound. Again, it's also open source, and it's a Node.js server that simply answers requests from web clients and turns them into requests into an Entwine organized software or data collection. And so this piece of software is what allows clients to be more flexible in how they make requests to whatever the server. And that allows them to do on-demand compression, so they could ask for data as compressed or not compressed depending on their capabilities. It allows them to do things like pass server-side filtering, only give me data that's classified as ground, for example, or only give me data that's classified as vegetation, and something that you couldn't necessarily do with just a tile collection. And then finally, the last piece of open source software here is Plasseyojs, which is a Clojure and JavaScript framework that is focused on large-scale aerial survey LiDAR, so the Denmarks and the Iowas, as opposed to kind of smaller-scale LiDAR. It allows image web service overlay, and it speaks Greyhound REST client, so it uses Greyhound to fetch and interact with its data. So I can't chew gum and walk at the same time, so I'm not going to live demo and talk, but I do have some movies I'm going to play, and then at the end I'll do some live demo during the discussion and answer period. So in this particular scenario, we're using Google's geocoder to search for the Empire State Building. This is the New York City collection. I think it was captured post-Sandy. And we zoom into the Empire State Building. The color imagery here in that scenario was coming from ArcGIS server's tile set. We modified the elevation shader to try to highlight some of the buildings here, and then we're going to back out and zoom into Statue of Liberty and be able to zoom in, zoom out, interact with the data, adjust the visualization. So in that scenario, I took and copied the URL. So as the user interacts with the data, the URL to the position and configuration of the visualization environment is maintained. And so users can copy that URL, send it to another user, and provide them an exact view of what they were looking at. So this is very useful in collaboration scenarios where you want to, say in a quality control scenario, where you wanted to show somebody, hey, go look at this piece of data and look into it and try to figure out why it's maybe needs to be edited or modified or so on. The next scenario is the country of Denmark's collection. So Denmark here has color information, but we're going to change again to the ArcGIS satellite imagery, and we're going to zoom in near the Copenhagen airport. And Netherlands LiDAR data is very nicely classified, so all the vegetation and roads and so on is classified. An advantage of having a point cloud web service like Greyhound is the client can make requests to the server in a fashion that answers their specific needs. So in this scenario, what we're going to do is we select a point to find out what its classification value is. In this case, it was 5, which is, I think, high vegetation. And then we're going to pass a filter back to our Greyhound service that says, hey, only give me back points that meet the classification value of 5. And then the Plasseyojs web application allows the user to mix different rendering filters or capability techniques onto the data. So in this scenario, we were blending both the ArcGIS tile set and the classification values together, and of course our filter. Remembering that this set was some 400 billion points in size. We don't need to interact with all 400 billion points at once. We can zoom in or interact with the patch or the level that we want, but we don't have to maintain an index or manage these thousands of files to be able to go touch all of this data. So one could imagine developing applications for things like quality control, looking at specific buildings, uses, earth structures, whatever kinds of things where you're hopping around looking at small bits of data. One could imagine building software tools, software capabilities on top of these open source tools to achieve that. There are also other clients available that speak Greyhound at the moment. So there's a software client, a WebGL browser-based software client called Poetry, which is much more focused on measurement, interrogation of the data inside your web browser, and I'll have a couple movies here in a second. And then the PDAL software itself has a client that can consume Greyhound services. So while this particular talk is focused on applications that are visualization oriented, so I'm looking at or visualizing data in the browser, the benefits and the benefit of organizing the data and providing these large collections of data as web services is software clients, it alleviates the need for these software clients to essentially manage their own tile and workflow schemes themselves. They can just simply access the data web service systems, the point cloud web services themselves. So, one could imagine software, so PDAL has the ability to do ground filtering, for example. One could imagine running an application in, on some server somewhere that, trundles through all all of the data in a point cloud web services for a large area, and fetches full depth data for patches and applies some ground algorithm to the data and then does something with that output. Or searching type algorithms, or vegetation assignment type algorithms. So in addition to this visualization oriented stuff, these services are reusable for processing scenarios as well. And again, we develop the services so that they're lossless in terms of the data that's inserted into them, because it might be some application like this that might use the data in some other way. And so the preservation of what was put into the box is important to preserve. There's also some, simply because it's a REST style HTTP server, you can simply make URL requests against the Greyhound client, or excuse me, the Greyhound server, and fetch data. And so a simple scenario like fetch a bounding box and give it to me as an LAS file or an LAZ file, is something that's very straightforward to write in Python. So there are other these kinds of scenarios that people writing little and small specialized tools with software environments like Python would be able to develop without having to have a lot of infrastructure around them for doing the data management piece. And that again is the point to hit home here is the management. The thing driving this organization is to alleviate the management of these very large collections of data. So this next scenario is the Poetry client. So again, looking at the same Greyhound service that was New York City. And in this scenario, we're going to create a 2D profile of the Brooklyn Bridge and the Williamsburg Bridge, I think. But so Poetry is a client that's oriented more towards interrogation and measurement and visualization of point cloud data. So whereas the Plasseyojs client is oriented, I think, more towards large-scale aerial collections and spatial bookmarking and kind of collaborative kinds of things. This the Poetry client has a slightly different focus in terms of interrogation oriented, being more oriented towards interrogation and measurement. So again, these capabilities that are completely browser-based, right? So instead of having an application for users to go measure something, they can simply log into a website where you as a data manager have provided these services for them to achieve some task, and put these services in front of them to be able to do what they need without having to install sophisticated software or get permission to install software, which potentially, depending on your operating environment, might be difficult. That's not to say a software application like this is able to replace any and every other Lidar visualization or interrogation tool. So you don't have lots of compute capability in your browser, and of course the modes of interaction that you have available to you can be limited. So kind of a thick client application certainly has its benefits, and so the advantage of organizing your point cloud data in services like this is, as some of these thicker clients start to come online with and participate in terms of implementing support for things like Greyhound services, they can dissolve this data management challenge of tens of thousands to a it's my hope that other vendors will be interested in these open source capabilities and start to implement them in their softwares. Another final scenario here is simply, so this is a mobile data collection in Iowa that was captured, and we're simply measuring the distance from the bottom of the bridge to the road. Again, Poetry is oriented towards measurement and interaction with the data. Slightly different take on how it does visualization, how users zoom and pan and manipulate the data. But if there are scenarios where interacting with the raw point cloud data has value for you, browser-based stuff, depending on the scenario, is potentially very useful to you. And these capabilities can be deployed today. Everything I've been discussing here is open source. The entire software stack, from being able to read and write, the different file formats with the PDAL software, or Poodle, either pronunciation is fine. The organization bit of the software, which is called Entwine, which takes these very large collections of data and organizes them into a single cohesive data structure. And then the web services component called Greyhound, which answers requests over the internet to that large structure of data that was organized by Entwine. And finally, browser-based or other visualization and exploitation environments that implement support for Greyhound point cloud web services. So kind of wrapping up here a little bit, so the advantages of these web services, first and foremost, is simply alleviating the data management burden for users for these very large collections. So, whether it's very large mobile collections, hundreds of miles of railroad mobile data, large collections of dense matched imagery point clouds, to this software stack, it's all just point clouds and stuff to manage. The software is designed and organized to be able to scale and operate in cloud computing environments. So, access to lots of data and lots of computing next to each other is potentially valuable, but it's open source software. So if you want to run this in your back office, or you want to run it on your desktop and just play around with it and see if you can build services yourself, the tools are available for you to do that. You're not limited by only running in the cloud or only running in on the desktop. And of course, the open source thing, there's no licensing cost here. So if you have services that become very popular, your cost structure is oriented towards answering all of those requests, not scaling your licensing with your popularity. Some benefits, or some use scenarios that we see for these point cloud web services. The first one is your state GIS clearinghouse that maintains either a mirror or a replica or the origination LiDAR data, aerial LiDAR data sets. Government agencies are the ones that have had the funding to acquire these large collections of data. Federal government organizations like Army Corps, USGS, maybe NOAA, that have very large holdings of point cloud data. That's where those are the groups that have funded the research and development of these capabilities, right? So we've been using them to provide data management solutions for Army Corps of Engineers. That's who's been supporting this, and so we see those organizations having strong desire to be able to use this data, and then of course international agencies, USGS or similar kinds of agencies in groups like Denmark, Canada, United Kingdom. We see the consumption of these services. Again, we've bootstrapped the thin client side of things towards collaboration and simply quick visualization of large collections. But the thick clients, start to need to catch up on being able to provide support for this as well. So, maybe something like your NV or Qt modeler, one could imagine being able to connect to a URL and it figures out, where you are and zooms in and allows you to interact with data over the internet, provided by some service, whether it's yourself or one of these agencies providing these services for you. Again, alleviating the data management burden, even for those users. The other thing is large-scale web services provides a consistent access and authorization story. So if you have sensitive data, that might be a strong issue for you, and allows you to manage your data access the same way you're managing access to other information. Finally, we see these capabilities being very, very useful in parallel processing and automation scenarios. So, the first step in many software exploitation algorithms is organize the data, either as some sort of spatial structure, cut the data into tiles, all of those kinds of scenarios. The Greyhound and Entwine software stack allows them to do that once and in addition to providing the data for visualization and interactive viewing, be able to provide that answer requests to software algorithms or automated systems that are essentially doing the same thing. Just a quick word of thanks to the U.S. Army Corps of Engineers, especially David Finnegan and Michael Smith at Cold Regions Research and Engineering Laboratory up in Hanover, New Hampshire. And then Jason Stoker and Rick Brown at USGS have been evaluating some of these capabilities and software techniques for potentially providing services like this for a U.S. Geological Survey. And then the various state agents, there's been various state agencies, either who have provided data or provided support in other ways like that. Folks in Denmark and so on. Thomas Knudsen and Christian Evers recently provided the Denmark data. Groups who provided the Netherlands data and so on. They have had interest in, because of these very large collections, looking at alternative ways to manage it. So this software is available for you to play with and interact on the internet, and so I'm going to do, I guess I'm going to answer a few questions here and do a little bit of live demo, which never works, but so I guess let's open up the floor to some questions, and David, and I'll switch over to my browser and show some of that.
Okay, so right now the first question that we have is, what issues might be there if we are behind a robust firewall? For example, not able to view most videos or stream programs.
So, okay, so the streaming software, so it's a browser-based application, so it just makes its requests over HTTP. So whatever the firewall and firewall maybe is not so much the issue as proxy might be an issue. So whatever the proxy scenario is in that particular, however your network is configured for typical web applications is going to be applicable here. There certainly is going to potentially be some issues with making lots of requests through a proxy or a firewall, but the technology itself is simple HTTP. So it's not connecting over a special socket. It's not connecting over a particular port that you need to punch a hole through a firewall to get. So those kinds of IT challenges are eliminated at least.
Okay, right now that's the only questions that we have, so let's watch the demo and we'll just wait for additional questions.
Okay, so one of the scenarios that I've found this sort of capability very useful for is many of these statewide or larger collections of LiDAR are not really looked at in aggregate. So we're looking at, hopefully you're all seeing Iowa here. So the Iowa collection, was acquired, I think there was 13 or 12, somebody from USGS could correct me, different contractors or at least subcontractors who flew LiDAR data in Iowa during its collection window. And, it's kind of assumed there's some variability in things, but it's, after you look at all the data in aggregate, it becomes quite clear that there starts to be some variability in how the data were acquired. So one of the things software like this allows us to do is, as I mentioned, was to be able to filter the data out. So, a common thing, at least by USGS base specification, is, the delivered data needs to, assign classification values to, say, ground and vegetation, and be able to assign classification values to noise, and the Iowa data preceded a lot of the base specification, of course. But so having the ability to look at these large collections of data in aggregate and be able to filter this data, is potentially useful to them. So this filter here is simply an AND filter that says so we can assign some values here, and as we can see, in this area in particular, down in southeast Iowa, some of the data was classified as noise and we were able to throw it out, but other data wasn't necessarily classified. So the ability to filter data, or filter the data for ground values, of course, which is a usage that many people want immediately, right? So not all of the data in Iowa has ground classification assigned to it, which might or might not be a problem for, say, a process that you were going to do across the entire state. Another capability that looking at these data in aggregate allow you to do is your kind of typical elevation modeling and scenario, large scale, state scale type stuff. We can do this particular application, again, this is the Plasseyojs application, is focused towards kind of data, or has capabilities for data fusion, and so in this scenario, I've adjusted the intensity values to blend with the, say, elevation data. So as it catches up to me here, we'll start to zoom in, and you can see high gain areas in your elevation, or excuse me, in your intensity. We can adjust the filtering to focus on adjust the rendering to focus on making the vegetative, or in this case it'd be forested areas, start to pop out. Maybe that's interesting to us for quality control or interrogation environment type scenarios. As we continue to zoom in here, our software client is figuring out what we are looking at and making requests against this web service and returning those data back to us and displaying them in our browser. We can, so on the Speckly website, there are a number of public resources that we have available to us. Another scenario that might be interesting to folks on the call here would be your typical mobile scenario. So this is a railway, I think in France, that was recently posted of some mobile data collection, and so it's a very detailed mobile collection that's allows if users want to do measurement or look at or do data quality, again, the ability, instead of simply a tile capability, if the data are classified, the ability to, all right, live demo gremlin. Anyway,
I have a few
ahead.
questions. So
Sure
for you, can you comment on the possibility of WebGL-based point cloud visualization using HMDBR setup?
HMVBR?
HMDBR setup.
I guess I'm not familiar with that acronym. So is that like VR kind of environment, or?
Yeah, I'm guessing that's what the person is asking. Yeah, a VR environment.
Okay, so so we have not been developing any VR clients to be able to use this, and I don't think we've actually tried any. But that's not to say that somebody taking, I know there are VR capabilities that are WebGL based. Taking the source code for this as a starting point and then looking to support that in those type environments would certainly be, again, the software is open source and available for people, motivated people to go and develop against and construct their services for. So, we haven't been developing that or working those capabilities, but that's not to say, again, the source code's available, people can go achieve that.
Next question, can I upload point clouds into the software for visualization?
So So for the large-scale services and the web services, the answer to that is no at this time. There is a WebGL client that kind of predated all of this stuff called Plasseyojs, which was kind of our very first version of the software at plas.io, and I think I switched to my back to my presentation to put the URLs up. That particular application allows you to copy or drop or open an LAS or LAZ file with your web browser and look at it in visualization environment. So it's actually looking at the file locally in your browser. It's not uploading it anywhere. We've been exploring developing capabilities to push data back up to a server or up to some piece of infrastructure. Nothing's been developed at this point. If there are organizations that are very interested in that or have software engineers who are willing to participate in developing those sorts of capabilities, we're very interested in talking to them though. It hasn't popped up the priority list, let's say, thus far. We've mostly been focusing on data that's already been acquired and kind of finalized, let's say. But I know that in situations that organizations are doing, say QC or editing, or they want to push back data, they need that sort of capability. So I can certainly see the need, just not there yet.
Are there training resources or instructions available for people wanting to learn how to implement these services?
Bits and pieces and fits and start. There are some kind of quick start tutorials on how to get started with Entwine and how to get started with Greyhound. So we are big users of Docker containerization, which allows us to provide it's kind of like a VM, but it's not a VM, right? So it's of a full stack of all of the software, PDAL and all of the bits to be able to read data and organize it in Entwine, and then serve that data using a Greyhound service. The browser components are simply JavaScript and HTML, so you can copy that to any web page that you want and connect those to whatever services that you want. So, one sort of integration scenario that I sort of desire is, the state clearinghouses or the national organizations that are looking to provide services for these kind of data would allow outside web applications to simply connect to it. That said, so there are, all of the software is open source, available on GitHub. If you file tickets about specific issues or you can't figure out how to do stuff or you get lost, there's some mailing list and some light, I would say, documentation at the moment. A new version of the Plasseyojs, the browser-based stuff, the visualization client is due very soon. That will have a number of documentations on kind of how to bootstrap yourself as a developer of the browser part. But the services part, it's pretty straightforward in that, you get a big directory of data and you run this program over it, and it goes and does its thing, and you can, you have flexibility to have 4 of them run at a time and cut it in pieces yourself, or just let it run at once, and then take its output then and simply serve it via HTTP with the Greyhound server. So the documentation, again, it's open source, so a very motivated person can go make it all work, but a not as motivated person, there is some stuff to start out. I would definitely agree it's a weak spot at the moment, and we're always looking for contributors. So if you don't have to contribute in simply software, if you contribute how-tos or descriptive documents or kind of a success scenario of how I was able to get going, those kinds of contributions are valuable to these projects as well.
Next question, is it possible to select an area and export it to a file? I mean, can you use the web tools and server to view a point cloud of a full country and then select an area that you want to download and work with that data locally on your computer?
So yeah, that's a frequently asked for thing. We just haven't built it yet. So the answer to that is it's a simple matter of programming, as they say. So the a tool to select the bounds of wherever it certainly can be written, and then essentially queue up those requests to the web service and write that out as an LAS or LAZ file. It's on the list anyway, just not done for the current version of the software. That's a frequent ask.
What are the benefits of using Entwine to organize the point cloud data as opposed to just using Poetry processing tool for organization?
So Poetry Converter, Entwine is a lot faster than Poetry Converter, and Entwine operates in parallel much better. So we've been working with Marcus, and his interest is in the visualization stuff. That doesn't mean other people participating in his project only care about the visualization, but his interest is in the visualization, and so he's been happy to outsource that particular aspect of the problem to somebody else. The philosophy of Poetry Converter is to essentially output a tile set, right? So when you process the data with Poetry Converter, you need to make some setting or suggestion about what that tile set sizes might be, and then it goes and processes the data. And so the Entwine Greyhound scenario, the client gets to control that. So so there's maybe a little bit of philosophical difference there. The current version, I think the current development version of Poetry has support for Greyhound services in it. So the ability for users, I recently saw a ticket in the open drone map repository where someone was using Entwine to process their data but then visualize it with new version of Poetry. So the capabilities are certainly there. And so, we've been working on the problem of, national or state scale LiDAR collections, whereas, Poetry Converter, there have been some groups that have attacked that with Poetry Converter, at great peril, maybe. But, so, maybe there's slightly a bit different focus in between those two softwares, but, we have been collaborating and still continue to collaborate on them.
Next question. For viewing the point cloud in Cesium, which workflow will you suggest?
So at the moment, there is an ability for Entwine to, so there's an option in Entwine to output, instead of its native format that you can serve with Greyhound, output 3D tiles format. So it'll organize data as 3D tiles. The point cloud storage and organization of 3D tiles is a little bit different than what we would typically do for just Entwine output, and it works a little bit differently. On our development queue is the ability to have Greyhound simply answer 3D tiles requests. That's not a software that's written at the moment, but it's on our development queue. For us, the ideal is to be able to just connect to one server and be able to answer all of these different data types. So that's something that's on our radar and we want to get to. We've also had some challenges getting, 100 billion or 500 billion point LiDAR collections in 3D tiles in Cesium is kind of prohibitive right now just because of how 3D tiles data format is structured for point cloud data. And so we've been working with the developers there to at least provide some input on maybe how things could be structured to make things work better in that scenario. So there's still some work to be done there. For like a New York city size collection, though, you can certainly output that as 3D tiles and be able to interact with it as point cloud data in Cesium. And there's been examples of people having success with that. Like I said, we want to get to the point where we can do answer 3D tiles point cloud requests right out of Greyhound. Not there at the moment, but it's on the radar.
Does the software require processing to generate indexes?
So yeah, so the Entwine component is, so what's going on there is we're taking that data and sorting it along a space filling curve, right? And so that process is easy to operate in parallel. You just cut up the areas into chunks and process them in chunks instead of as one contiguous thing. But you do need to process the data. So a typical statewide collection might, when I'm saying 30,000 tiles, what's going on there is they might have cut that data into, say, 1 kilometer by 1 kilometer chunks. And some of those 1 kilometer chunks are have 2 million points in them, and some of them have 100,000 points in them, and some of them have 10 million points in them, right? And so when Entwine's organizing those data so that that density is consistent and high, and a software is able to take a bounding query box and hierarchically traverse the tree to be able to find which points fit within that hierarchy. So yes, there is a processing step that's happening here. It's important to recognize or realize that Entwine, when we do organize the data in Entwine, though, it is a functional requirement that the software, the data as it was dumped in, be able to be reproduced. So for typical linear scan LiDAR data, maybe the ordering of the points has meaning, for example, right? And so lossless to us means being able to potentially reconstruct that ordering as well, so that sort of information is optionally stored as you organize the data. And then, of course, the coordinates themselves are not wiggled or moved. Every coordinate that's put in is stored in the tree itself, so it's lossless. These have been requirements for that particular software. So it's not, we've been using it for these large-scale services. I think there's maybe some discussion to have about looking at it in terms of formatting and so on, but that's something that kind of needs to be worked, by other folks coming into the program. And again, it's open source. It's on GitHub. You can log in, start filing tickets, asking questions, find out more by going to these websites.
Next question, is Greyhound responsible for organizing LAS data into an OC tree?
Entwine is, Entwine organizes the data, but so the like aerial LiDAR data is horizontal. I call it horizontally biased, right? So you have lots of data in the horizontal direction and not as many values in the Z dimension, right? And so storing the data simply in an OC tree in that scenario tends to be a little bit wasteful, because you end up with lots of these splits in the Z direction that you don't necessarily need for an OC tree. So there are some optimizations that are allowed or users can configure to make things work better in different scenarios. But like the railroad scenario that I showed, a typical OC tree in that scenario works great, right? It might be very deep depending on how dense the data was. But so the Greyhound, what Greyhound does is it answers requests, like whatever's underneath it, it behaves like an OC tree, so that if your software that you wrote wants to make frustum queries against something that behaves like an OC tree because it's a convenient thing for them to do, that's what Greyhound expects to answer for people.
If we want to generate derivative products taken from the point cloud, could we use the existing services or on-demand access to those point clouds, or we will need to create an instance of the application and the point cloud as its own files?
So for derivative services, I think the answer to that is yes, you can use these services directly to construct software capabilities to build, say you want slope surfaces, or you want to do ground classification or something like this. Our sort of intention is to be able to start developing software that leverages these web service organizations of software, of which Greyhound is an actual live implementation that you can use today, to be able to write services that operate on that data. The output of them, so say they derive a new ground classified point cloud, or they derive a geotiff slope or something like this, there's no pushback of that up to Greyhound or Entwine or anything like that. So the data management after the fact at this point is still kind of on you. As I mentioned earlier, though, we are, the idea to push data back to us is certainly of interest, and we'd be looking for other software engineers, other folks who that's really a priority for them. For the groups that we work with, that hasn't been as big a priority at the moment. Not to say it won't be. So that's kind of the story right now with that stuff. One of the things we found in these large point cloud warehousing scenarios is the original data never goes away anyway. So as delivered data, or some contracting officer signs off on the data, it's on a hard drive somewhere. It doesn't ever get blown away. So those bits always end up sticking around no matter what you try to do with them. And so, being able to organize the data in web services like this, potentially provides some more utility, at least in terms of just visual interaction with the data and verification, but also these other services.
Is there any estimated date for the ability of the Docker containers? We're looking to develop an open source processing pipeline for Canopy maps, and will be very much like to be able to access the point cloud on demand.
The Docker containers are available today. So if you go to these links that I'm showing on the browser or on the PowerPoint here, if you go to entwine.io and greyhound.io, they'll eventually point you into the GitHub stuff. But the Docker containers, to be able to set this up and start playing with these services, certainly at desktop scale, are available today. And as a developer, you're going to have to do some more lifting on your own to get to kind of cloud scales type stuff. But if it's a good fit for a Canopy scenario, right? So the first part of your Canopy problem is build an index, right? And so being able to interact with that and this sort of approach, I could see how that would be very interesting. So the software is available, and then as open source software, build it yourself, no batteries included. But then the Docker containers, which are full integrations of Entwine or Greyhound and all of their dependencies, and configured in a way that you simply just run a command and the software can run. And Docker runs on Windows 10, and it runs, of course, on Linux or Mac OS 10. So, your ability to simply just execute the services and build data, that's the smoothest way for you to do that without having to kind of start from scratch and build it yourself. Maybe one more question?
Yeah, we have two more.
Okay.
Would you give us kind of a cost estimate associated with something like a state on the cloud, something like a stateside data set? How much you think it will cost on your experience?
So the closest one I remember here is the Netherlands. So the Netherlands was 2+ terabytes, I think. So to organize the data with Entwine, we processed that data with 30 machines that each had 32 cores, and because we were trying to see if we could do it, how fast we could do it. And so we were able to process that data in a little over 9 hours. And the run cost of that computing was about $420 or something. So the organization bit of that particular stage was 400 something. It output a data collection that it's a little bit bigger than straight LAC because as I mentioned, we want to store a flexible schema, so it's not just LAZ schema. So the data compression is not as efficient as LAZ. It's still pretty efficient compared to like Deflate or anything else, but it's not LAZ. And so that bumps up the storage to something like 2.5 or 3 terabytes of disk at-rest disk storage. So you're invested $400 to organize the data, and then it's a roughly for commercial AWS, it's roughly $40 a terabyte per month to have it sit there. And then after that, it's simply your, however many requests, you're answering web requests at that point. So if it's, very highly sought after and you have lots of demand, your scaling story is going to be that. But so that's, kind of an, in comparison to how many millions of dollars it cost them to acquire the data, $400 and $40 or $120 a month isn't too terrible. And so, but, that's kind of the scale at which some of these costs might be for, different states.
And with that one, you answered the last question. It was if the style files was going to increase when you use Entwine to generate the indexing. Yeah,
so that's something we've been working on a little bit. So as I mentioned in the presentation, the tools we've developed make the LAZ compression work in a web browser. And so LAZ is a compression model and an arithmetic encoder. And so when Entwine processes the data, it simply compresses each field, X, Y, Z, intensity, classification. It uses the arithmetic encoder to compress each field individually. It doesn't compress them as units. And so LAZ compresses them as units. And of course, the LAS model is kind of fluffy because you have points with lots of the same values except for return number, for example. And so they compress quite well. In the way Entwine's using the encoder, that you don't get those advantage. So there's it's a little bit bigger than that. But in exchange for that, we can compress any format. And so not just LAZ, so for the groups with the Army Corps that we work with, the BPF format is quite common. You have database-oriented formats like PG Point Cloud and Oracle Spatial or Oracle Point Cloud that we can store data in using this same just arithmetic encoder of LAZ. So there's been a little bit of proliferation of that. For us, the driver has been being able to do that, a flexible format and be able to do it both server side and client side, where client equals JavaScript in a browser, and so that's what's driven that.
And that was our last question. So I want to thank you. It was an excellent presentation. If people have more questions, feel free to email them to the registration email, and I'll forward them to Howard, and then we'll email back everyone their answers.
Thank you very much.
And I want to remind everyone that our next GeoByte is in February 24, and that one will be on projections. Thank you, everyone.